Hello, this is my iteration of the differential equations or Math 321 final project, created and voiced by Ray Brunken. The subject of the calculations for this project will be a Bamboo Labs P1S 3D printer. We will be measuring the temperature of the hot end, which is a part of the extruder of the 3D printer. For this project, I will be collecting the data through the Bamboo Labs built-in program known as Bamboo Studio. This program comes with each and every one of the Bamboo Labs 3D printer lineup. This program provides real-time hot end temperatures as well as a couple different controls for a couple different parameters for 3D printing purposes. This data will then be frame by frame analyzed to create the data set. As far as the parameters I've set for this testing procedure, I've ensured the glass door has been closed, as well as all of the fans and ventilation equipment have been turned off. Later down the road, this will create fewer variables for us, as well as eliminate any draft that could be present. When performing frame-by-frame analysis of the data, I have these two outcomes, being the table on the left and the graph on the right. This was the hardest part, as it was very tedious. For the exponential model, this is just a rough estimate to compare to the differential equation that we will come out with later. This has a formula of y equals a times e to the power of b times x, where b equals the negative k value. When graphing this in Excel, we come out with a k value of 0.006. Again, this will be a rough estimate to compare to our differential model later. Upon graphing more and more data points, I have discovered that the k value fluctuates from 0.006 down to 0.004 as I add more points. This is likely explained by the atmospheric temperature changing as the heat from the hot end is radiating off of it. As far as formulas being used for this project, I will be using Newton's law of cooling. The temperature of the atmosphere is set at 23 degrees Celsius, as indicated by the print bed temperature 23 on the right, and the initial temp temperature will be set at 250 degrees Celsius, which is the average printing temperature for the filament that I have been using. The variable t will be time in seconds, and we will be solving for k. Using this formula and a point on our data, we come out with a k value of 0.00663, so just around the 0.006 estimate that we first achieved. When using later data points in the graph, we find that our k value has fluctuated down to 0.00620, which is a smaller change than our exponential model has predicted. Even when using a third, even later data point in the graph, we find that our k value has fluctuated all the way down to 0.00576, which is a greater decrease than from our first point to our second point. This is again likely explained by the change in the atmospheric temperature. With this k value being found to be around 0.006, a nice round number, we finally have our final model seen here. The 0.006 indicates a very slow cooling rate, which could be explained by the lack of ventilation, as well as the very thick, high temperature resistant insulating rubber around the hot end. When we plug this 0.006 k value into our equation along with a assigned t value, we can find the predicted temperature of the hot end. When we plug in time 60, for example, we find that the temperature of our model is 181.07 degrees Celsius. This is slightly off by 5 or 6 degrees, however. When using the initial and more specific k value of 0.00663, we find that our prediction is significantly more accurate, as it is only 1.17 degrees Celsius off. However, this error could be explained by sensor rounding in the program. This will be later explained in the next slide. As far as potential points of error in the procedure, as I previously mentioned, the software does round to the nearest degree when displaying its temperature. As well as this, the atmospheric temperature in the chamber is not constant and is changed by the radiated heat from the hot end. This temperature is maintained by the lack of ventilation in the chamber as well as the insulation around the hot end itself. An additional potential point of error would be the limited temperature refresh rate of the program. This is indicated by the broader changes in the temperature at earlier points in the data, as only the recorded temperatures in the data were the temperatures resulting from the program itself. Additional to this, the refresh intervals may have been changed and optimized by the software to improve performance. Regarding the application of this model, it would be suitable for the 3D printing application as a plus or minus 5-degree tolerance is suitable for most 3D printing applications.